In this example, we will start with the simple case of a single long half-life radionuclide, cesium-137, a half-life of 30 years. Using a time-varying emission rate and with the radiological dispersion calculation internal to HiSplit. The focus for this and the 5 other examples will be the accident at the Fukushima nuclear power plant, and specifically on the 2-day period, March 14th and 15th, a period that was most critical for the population dose due to the significant radionuclide releases and accompanying onshore flow. To get started, download the following 4 files to your computer's working directory from hisplit.com. The WRF meteorological data, the JAEA cesium-137 measurements at Tokai, the emit times, which is a series of emissions, and one of the emit_time scripts for either Unix, Mac, or Windows operating systems. The default configuration for HiSplit sets the emission rate within the control file as a constant value over the emission period. But if time-varying emissions are required, then an emit times file needs to be defined. For this example, the emit times file has already been configured based on data from the United Nations Scientific Committee on the Effects of Atomic Radiation, the acronym which is UNSCEAR, with the hourly rates valid over sequential 3-hour periods. When decay is defined for a pollutant in HiSplit, a radionuclide starts to decay only after it has been released. But the values in emit times are based upon the radionuclide inventory in the reactor at the time fission stopped, 6 UTC, 11 March 2011, the time of the earthquake. So unless the emission rates are decayed to the time of release, we cannot correctly apply decay within the HiSplit calculation. The decay issue will be addressed in more detail in the next section. But for now, and because of cesium-137's long half-life and the short duration of the simulation, we will disregard radioactive decay. But this simplification is clearly not an option for any of the shorter half-life radionuclides. Now open the emit time script, and if needed, edit the location of the HiSplit directory, and if you are on a Linux system, the location of your default web browser, which is required to open the SVG graphics created by HiSplit. Browser information is not required for Mac or Windows computers. The control file is created within the script, with many of the key parameters that configured the script for the Fukushima accident set at the beginning, such as the start time, release location and height, run duration, and meteorology file name. The simulation is set for a 3-day period starting March 14, 2011, which encompasses the maximum emissions, the first 48 hours, and an additional day for those particles already released to impact the concentration grid. The height parameter defines a vertical line source between 1 to 100 meters as a compromise between the ground level and elevated releases. The CPAR, cesium particle, emissions are set to 0 to ensure that the model fails if the records in the emit times file are not properly configured. The concentration, deposition, and subsequent dose grid resolution is set to 0.05 degrees, or about 5 kilometers, with output as 3-hour averages for the deposition level 0 and the air concentration layer 0 to 100 meters. The cesium pollutant is defined as a generic particle by non-zero values in the size field and with a forced dry rather than computed deposition velocity of 0.1 centimeters per second. Wet removal is defined using the default values for particles. Many high-split simulations required some customization of the name list variables. Those not at their default values are defined in the file setup.cfg. Because our interest lies more closely to those particles near the ground, for these simulations, we fixed the integration time step at 5 minutes to get consistent wall clock times and avoid the short time step penalty for particles that wander above the boundary layer into regions of faster winds. The particle release rate is fixed at 2,500 particles per hour. The value is per hour when negative, rather than the total over the release period when the value is positive. Also, we limited the particle age to 24 hours because we are not interested in particles that are no longer over land. Still, by the end of the simulation, there will be about 55,000 particles on the domain. Clearly, finer resolution concentration grids, either in space or time, would require a much larger particle release rate. When the e-file variable is not blank, that is, emit times, will be opened and the emission values will replace those defined in the control file. In subsequent examples, we will not be going over the script in the same level of detail. Only critical changes will be addressed as needed. Now go ahead and execute emit time. You may want to pause the video until your simulation ends, at which point you will be prompted to continue with the graphics section. Enter yes. For this presentation, the script has already reached this point in another window. The post-processing section, all the commands after the high-split execution, may include data conversions as well as graphics. One of the files you downloaded is the time series of cesium-137 measurements at the Japan Atomic Energy Agency site at Tokai Mura. This file has been converted to the datum format, the details of which are addressed in the basic high-split tutorial. The first post-processing program, C2datum, converts the high-split output file fdnpp.bin to datum format using the measured data file JAEA_C137.txt as a template, replacing the measured values with high-split model predictions output to tokai.txt. Selecting the output level array index number 2, the 0 to 100 meter layer, and converting concentrations from becquerel to millibecquerel. Both files are then displayed as a time series by the time plot program, using log scaling for the ordinate values. The red line shows the model predictions, and the black line the measurements. The second graphic, the total cesium-137 deposition, is created by the constplot program by summing all the 3-hour deposition periods together, the R3 option, in the high-split output file fdnpp.bin to generate a total deposition map, plot_dose.html, at the end of the simulation period. Note that for species with shorter half-lives, the total accumulated deposition at the end would be an overestimate of the actual values that might be measured at that time, because the deposition for all the previous time periods have not been decayed after they have been written to the output file. The last two frames are dose, also created by Kant's plot by entering a dose conversion factor for deposition, rem per hour per becquerel per meter squared, and air concentration, rem per hour per becquerel per cubic meter, in the -y-x command line fields. To get rem rather than rem per hour, those factors could be further multiplied by 3 hours. As you scroll through the dose output graphics, note that the R2 option causes the deposition pattern to accumulate each time whilst the air concentrations meander about with the changing wind directions. Dose conversion factors can be obtained from the Environmental Protection Agency or the Department of Energy. To obtain total dose, the air dose and ground dose must be added together. Other programs are required to merge the deposition and air dose components. This will be addressed in a future section. This concludes the simple dose example. Next, you will learn how to set up a single transfer coefficient matrix.